So Hal will start at 9:30 at the usual time, and but things may change, and so check your email in the morning. And if you don't hear anything, show up here. So I'll leave it to you to introduce December.
Yeah. Okay. So officially, the typhoon day will come or not. I mean, to have a break or not will be announced around 10 p.m. today. So we don't know exactly what's going to happen. So please check the email. Tomorrow the lecture will end at noon, 12 o'clock. So we will not provide another lunch box.
Right.
If you can have whatever you want. Okay. Okay. So let's have the last lecture today. It's given by another TA from National Chicago University. He will talk about strong monodromy conjectures for monomial ideals on Toric varieties.
Okay, thank you very much. It's my pleasure to thank the organizer and Professor Cox and Hal is not here, and Lynn and everyone here. And we have 1-2 weeks already, right? And today, I'd like to talk about something that is called monodromy conjecture. Okay. And I will try to give you some background of that, but just a little bit, because there's a long history about this, and then there are lots of things behind that. But mostly I will focus on the Toric analog of this theory, that you can sort of formulate a similar conjecture for Toric variety. Okay. And let me just start. So there are, let's say, two players here. So we are going to talk about B functions on Toric variety and the so-called motivic zeta function for Toric variety. And I want to relate these two functions, okay, the root of B function and the pole of the zeta function. Okay. And here's a little bit history, just a tiny bit of it. So let's consider a non-constant polynomial with integer coefficient, and fix a prime p. Okay, so I have this. Okay. And we consider the number of solutions of f in Z mod Pm, and we let n varies. Okay, so Z mod Pm to the n. Okay, we have n coordinates. All right, and then consider this so-called Igusa Poincare series. Okay, so this is a generating series associated to this number of solutions, and the so-called Igusa zeta function is actually a transformation of this Q of T here. I will not expand too much about this transformation here, but I will mention a little bit. Let me see. So, right. So, let me just speak a little bit about this transformation, not the full detail, but so the thing is, you look at f as a polynomial in the ring of p-active integers, okay, and then you consider similar, like the number of solution and this generating function thing. So how do I? Okay, and okay, so in a for the ring of p-active integer, you have a variation defined by p, and then you have a way. So it's well known that the ring of integer is complete with respect to this variation. So variation gives you a metric, and this is a nice field, complete field, and then you can define some notion similar to like what you learn in real analysis, like the measure of a subset in Z. So the ring of integer, but you have n coordinate. Okay, so you can do measure theory here, and you can do integration on this set. So Igusa try to transform this generating series in this zeta function form, and this can actually be written as some integration, p-adic integration. Okay, and which I'm not going to talk about that, but later on we will see that there is an analog in character 0 setting, which is called a motivic integration. And if you sort of spell out the definition and try to see the analog between, so let me write something here. So we have, let's see here. Like the p-adic integer is the inverse limit of z mod pz. And actually you can write this here. And the motivic analog is really the, like k is character 0. Then you have analogous inverse limit of this one. So let's say this is n plus 1. Okay, and the full story can be imitated or maybe generalized to this setting, character 0 setting. Okay, and you will see more about this later. But let me just continue this p-adic theory here. That Igusa proved that this zeta function here is actually a rational function in T. And here T is P to the negative S. Okay. And and now I'm turning to another notion, the B function. Okay. So again we have a non-constant polynomial. So I'm sort of packing many things together. So okay. So there's a theorem of Bernstein and Saito, which says you can find, so for this polynomial f, you can find a polynomial function in CS. So S is a new variable, okay, and it's not accident that these two S are the same. I mean, we will talk about this later, but I just said that the roots are related to the poles of this zeta function. But okay, the theorem of Bernstein and Saito independently says that there is a polynomial Ps and differential operator. So here D is the wild algebra. So for those you haven't seen this before, so right. So D is the wild algebra. So it's somehow join the polynomial with the derivations. And you look at this commutative ring, non-commutative rings. So you can find a differential operator and a Bs, a non-constant polynomial Bs, so that this functional equation holds for all A. Okay. So I won't say much about this, but this is kind of doing this a change of variable in integration theory. Okay. So as long as you have this formula, it's nice to do integration. Okay. And okay, so the so-called V function associated to F is the monic polynomial of smallest degree of such Vs. So they exist in non-zero one, and the monic polynomial with smallest degree is called B function, and we denote it by Bf of S. And this, seemingly relevant two notions here, they have actually very nice relation here. So let's say when F is smooth over Z, then one can show that the B function is S plus 1. Okay. So because later on I will be more technical and many new notions, so maybe let me do some computation here. Okay. So that's all right. So let's try to right. So So we need this functional equation. So if we plug in, let's say A is 0 here. So if A is -1, so you got P0. So here P is a differential operator, and so A is -1, have F to the A plus 1, so F to the 0 is 1. So you differentiate some constant, this is 0. But if you have this functional equation, you should have B of, so -1. Yes. So this means -1 is always a root of B function. And this, I mean, for any polynomial, okay? But for F smooth, sorry, maybe I'm writing too small, but let's see. Then you actually have like the common vanishing locus is empty. So let's say F. So this is the first partial derivative. So this means you have a relation between the polynomial here. So let me write it down. So 1 is C0F plus C1 del 1F. Cn del F. Okay. So from here you can actually write down the functional equation for smooth F. So it is. I will let you to check that this functional equation holds. So right. So C0. This is S plus 1. Okay, so here this is a candidate for BS, but you know S plus 1 always divide BF of S, the B function. So this implies for smooth case, the B function is always S plus 1. And which means, and this is actually if-and only. Okay. So, but you have to work harder to do the other direction. But the point is that the B function divided by S plus 1, the rest of them, there's another theorem by Kashiwara that says this B function, the root of B function are always rational numbers. Okay, and so the information about the B function divided by S1 measures the singularity of F. That's the point here. All right, and the other ingredient for this item here is that when F is smooth, you can so when F is smooth, so smooth over Z, but we do, for what I'm writing here, we do want it to be smooth over some, like for some P, after modular P. And after that, like for larger P, it will be smooth, okay? But let me just be vague that I'm writing that for F smooth, then one can show that the number of solution, I might be mistaken somewhere, but it's like P to the M minus 1 or M, let's say M minus 1 and N1. So the number of solution modular PM is actually determined by the number of solution modular P, okay, if F is smooth. So this is like,
Sort of like Hensel's lemma.
yeah, and so somehow this is cylinder, okay, right. But yeah, there are details about this. I'm just stating some results. So from here you can, so the point corollary series it's actually determined by n1 of f. So this is why you can write q of t in this form. 1 minus p to the n minus 1. But there might be some error here, but yeah, okay. But my point is, you can, so you plug in q of t here, you can show that the poles of the zeta function when f is smooth is of this form. And we really care about the real part of this. Okay. And the conjecture of Igusa says that the real part of the pole of zeta function is the root of b function, which for smooth case this is true. We just prove it. Omit many details. Okay. Okay. So Igusa's conjecture states like this. Okay. So we relate zeta function and b function. Okay. And I have very few common, but it's only known in very few cases, and it's open for like 30 or maybe 40 years. Okay. And original conjecture has to do with the so-called monodromy eigenvalue, which is some topological notion associated to f. Okay. So it somehow relates to, I mean, you have number theory and you have singularity theory and topology. And b function has to do with this eigenvalue, but I will not talk about this. But our player here is a generalization of zeta function, p-adic zeta function, which is called the motivic zeta function, and this work in character 0. And this is a serious work by Neff and Rozier. And there is a survey of Nikkais, which states, I didn't verify the proof, but which states if you prove an analog for a motivic version of Igusa conjecture, so you can do similar conjecture, like you relate the pole of motivic zeta function to the b function. Okay. Then that will imply the ordinate, like p-adic monodromy conjecture. Okay. So somehow this is more general. Okay. But it requires lots of work, like you have to do reduction of p. Okay. And I mean, this is just advertised that we were going to look at toric motivic zeta function, and this is important. And again, also we so far we only talk about one function, but this notion of motivic zeta function can be generalized to ideal. Okay, so you hand me a set of generators. We have a notion of motivic zeta function. Okay, and the other side, the b function, is, I think, generalized. I want to say recently, but it's probably not too recent. Okay, so it's generalized by Budur-Mustață-Saito for ideals in smooth varieties. Okay, so I like Toric variety, and like the way I see Toric variety is it mostly is not smooth, and so you have many things to work on. And I used to work on differential operator on Toric varieties. Okay, so the first thing come up to me is like, can we do this similar construction for Toric variety? Okay. But before that, let me first recall the result of b function, like the Budur-Mustață-Saito result. Okay, but here's what I'm going to do. So I will recall their result, like a generalization to ideals. But this is somehow technical, so I probably went through it very quick. And well, so the story is that so for affine space, so you sort of view Toric variety as an analog of affine space, and on affine space, the differential operator are the well algebras. Okay, so for Toric variety, you have a you have a definition for differential operator by Grothendieck, and one have a computatorial description for the differential operators. So once you've seen the construction of B function, you might think that maybe I can use the differential operator on Toric variety and do similar construction, and to obtain the B function for Toric variety. And this is first part. And the second part is that the motivic zeta function is actually defined for any algebraic variety. So how about we write down the motivic zeta function for Toric varieties? Okay. So this is two part, and we try to relate the root of B function and the pole of this zeta function here. And before that, I should mention that Howell, Mustață, and Yuan, they do similar things. So they consider monomial ideal, the torus invariant ideal on the affine space. And remember, we have, so for ideal in smooth ring, you can talk about B function. That's work of Budur-Mustață-Saito. And they also compute p-adic zeta function for monomial ideal on affine space. So the way that they define the p-adic zeta function is mimic the Igusa's p-adic zeta function using the Hahn measure on the ring of integer. And I mean, original one is defined for one polynomial, but this is, I mean, it's easy to generalize to the monomial ideal case. And they show that the pole of Igusa zeta function, the real part of the pole of Igusa zeta function for monomial ideal in affine space is the root of B function. So they show that in smooth case, like in monomial ideal in affine space. So the rest part of the talk, I will hopefully explain some like joint work with Chinrui Lai, that we can compute a toric motivic zeta function, and then we actually have an example that the pole does not give you a root of B function. But so we can compute it, and we have a counterexample for the conjecture, and under some nice condition, we can still produce, like from the pole of zeta function, we can still produce root for B function. So this is roughly the outline of the talk, but there are many technical issues after that. So first, let me try to construct this B function here. But okay, and I think I should apologize that the sigma here is not a fan. Okay. Right. And so sigma in this talk would be the real, like the cone for affine space. Okay. And D is the wild algebra, and we consider a ideal. And I don't think I want to explain this. So there is a analogous construction for functional equation in ideal case. And for those you want to study in more detail about this, so this Ti is you raise the power to up to, you raise the power up, 1 up, and Ti minus is you subtract the power. Okay. So you have this similar action, and if you have R generator in the ideals, you have to introduce R variables. Not like the for one polynomial case, you only use S, but here you have many variables. And the amazing thing is that Budur-Mustață-Saito, they can show that you can actually find a polynomial in S, but here S is, this is curly S, this is sum of the variables. And they show that there is a polynomial in S, in this single variable, and with some, like this is similar functional equation, but you have, so you have differential operator acting on f to the s plus 1, because you see there's a ti action here, and then you get something f to the s, okay, times the polynomial. And this polynomial with smallest degree, monic 1, is the B function for ideal. And a nice thing is that, I mean, this B function does not depend on the generating set. And these are hard to prove, okay? I mean, you have B filtration thing, but the way I look at this, I mean, I feel this is very complicated, but you see from the functional equation here, what you do is you differentiating something and with respect to the powers. So I mean, when you differentiate, you only work, you sort of operate on the powers. Okay, so once you have seen differential operator on Toric variety, you might think this functional equation might make sense. Like you might get similar information if you look at Toric analog of this functional equation. Okay. So this PI is chosen from the wire algebra. Okay. So what if we do the same thing, but replace the wire algebra by the ring of differential operator on Toric variety? And then, I mean, I have to replace the polynomial ring by the normal semigroup ring. Okay, and then I can, I mean, we still have, like, you have R generators, so we still have this S here. Okay, so you can do similar construction. Okay, so this is what we do. But before that, I have to show you what differential operator on Toric variety. And here's another example that I want to do some explicit computation. So we start with a pointed rational polyhedral cone, and we have this normal same group here. And the first thing you realize is that okay, so I mean, I think the first question should be, what should be a differential operator for commutative ring over a commutative ring? Okay. And so there's a iterate definition of Grothendieck, and if you spell that definition out, you can show that the differential operator of this the ring of so this is the ring of the torus is actually, you just invert the x of the wire algebra. Okay, so this is the first thing. You have to do some work for this, but so basically the differential operator commute with localization. So first, I mean, this is already written down, so I don't want to write anything, but the ring of differential operator of k z to the d is this. You inverting xi of the wire algebra, but somehow we want to look at this in different forms. So we sort of moving the x to the del's and writing the theta. So write the theta I is the del x times del. Okay. So this ring equals to this ring. Okay. But when you look at this, you can show that the differential operator of normal semi-group ring, actually you don't have to assume normality here. So this formula also works for any ring of R5 toric variety. Okay? But if you assume normality, I mean you have nicer description. Okay? So here you can show, I mean this is not straightforward, but you can show that the differential operator on the kz to the d here, if you operate on the normal semi-group ring and it stay in the semi-group ring, if delta satisfies this condition here, then it will be a differential operator on the normal semi-group ring. Okay. And if you spell it out, you will have, so you see you have a z to the d gradient here. So you also have a z to the d gradient for the ring of differential operator on normal semi-group ring. And let me explain a little bit about this here. So you have z to the d gradient on each component. You have x to the u. U is into z to the d, and here you have something in theta. Remember, theta is x delta, x times delta. But what are the stuff in here? It should be those polynomial in theta, but vanishing on this set here. Okay. So if you spell this out, it will be the condition right here. But let me give you an example. So like if you have a if you have polynomial ring, like if you have polynomial ring, you expect you get a wild algebra, right? So what do I want to write? So differential operator of k. So k should be characteristic 0, and say n to the d. And this is direct sum of those u, xu, and you have something here. Okay. F theta and f vanish omega u, right? Whatever. Omega. Or it depends on u, so I should write u, but okay. But let's do something here. So you see this omega a. I mean, this is related to u, so I should write. So n is na. So it's the lattice point in the semigroup, but not in the shift of the semigroup by negative u. Okay. So if u is already in the semigroup, you will actually get every theta. Okay. So if u in the semigroup here, you actually get theta. So this part x, the component here is xu times the whole polynomial ring in theta. Sorry, what am I writing here? Because this is empty set if u is in the semigroup ring. Okay. Sorry, this should be empty. Sorry. Okay, and that's like if u is like what do I want negative 1, 0, right? So x to the negative 1. Okay, so maybe, yeah, so I think I'm doing something for b equal to 2. So if u is negative 1, 0, you have x to the negative 1, and here you are considering the, like, there's one line missing, so this line should be n to the substrate. I mean, I'll let you write down, fill out the detail here. So, but I may be mistaken somewhere, but here you should get theta. Okay. I mean, the ideal generated by theta. Okay. So, but this is del. Okay. So for polynomial ring, you do get the Weyl algebra back. Okay. But for normal symmetrical ring, you get many different things. And it's not clear that whether this big ring is Noetherian, but actually for normal symmetrical ring it is. One should prove that. But for non-normal symmetrical ring, it could be non-Noetherian. So this ring might be very, very huge. Okay. Okay. So this is my comment for this. These are my comment for this. But you see, you have a z to the d gradient. Okay. So it's not reasonable to hope that the operation here give you some information about v function on Toric variety. And this is what I do with Laura Matsevich. So let me see what I. Right. So I have to probably run quick about this. So you use the functional equation, but for Toric variety, and use this ring differential operator. And all you do is you you have z to the d gradient, so you actually operating on the lattice point, something like that. Okay. All right. So we get a notion of b function, same construction and independent of the generating set. Okay. But the way we prove that this is independent of generating set is that we relate this b function into certain monomial ideal, into certain b function for monomial ideal on a affine space. And because the result of Budur-Mustață-Saito, this is unique up to your choice of generators. So our theorem implies that this is independent of choice of generators. Okay. So this is what we do. So we have an ideal in Toric variety, right? And we just do a transformation here. So I have a map F, and so F actually sent U to a vector in R to the n. So my Toric variety, the cone of my Toric variety live in some d-dimensional thing. Okay, I assume my Toric variety has dimension d, but we look at, so for each U in R, we look at the distance between U and the facet of the Toric variety. So you pair with the VI technically. So it's so VI is a dual in so VI should be in sigma. Okay, the minimal generator of the primitive generator on the ray of sigma, and my U here should in M or MR. Okay. So this map actually induce a map. So here n should be the number of the facet of sigma, and this map induce a ring homomorphism between so this is a polynomial ring, and this is our semi-equal ring, homo-semi-equal ring. Okay. So I have a ring homomorphism. Okay. So this actually embed the original semi-equal ring to a larger semi-equal ring as a sub-semi-equal. Okay. Right? And so you have a polynomial ring, and you just naively, like, you have a generator. So I have a generator for ideal here. Let's start with a monomial ideal. Okay. So the generator are represented by lattice point, and you just send the lattice point to the polynomial here, and you consider a corresponding ideal in the polynomial ring. Not in the image of the ring, not in the whole polynomial ring. So you're extending the ring. Okay. And the amazing thing is that one can show that the operation matches. Like if you do operate, like if you do the functional equation for Toric variety for semi-equal ring here, it's the same as doing the functional equation on the polynomial here. Okay. You have to do some work, but it just happened that they are the same. Okay. So we have a notion for B function on Toric variety, but what's the matter? I mean, you just if you just have that, you're mimicking some algebraic operation. Okay, but one nice thing about this B function is that we can show that so it is known classically that the root of B function has to do with jumping coefficient of multiply ideals. So the multiply ideal is a certain ideal in the structure shift of so it's a certain ideal that measure the singularity of your variety and your specified ideal I. Okay. So this is defined by using the resolution of singularity of the pair. Okay. And classically it's known for like the B function, the root of the B function has to do with the jumping number of the ideals. So you have many multiply ideals, and they are jumps. Okay. But for Toric here, one can also compute multiply ideal, and this is actually written in the book. Okay, I think chapter 13. I don't remember 14. And one can show that the B function we construct, the root of B function are also related to the jumping coefficient of the multiply ideal. Okay. And this is nice. And okay, here is some few comment, but I don't want to spend time on this. Also, there's a comment that one can specifically write the root of B function for monomial ideal on polynomial ring using combinatorial data of J. So J is a polynomial ideal on polynomial ring. And I think, I think I spent too much time. So I have to explain to you what the motivic zeta function is, and maybe in the last minute I will say what the result is, but let's spend time on this. Okay. So this is an analog for periodic integration. So we have to work in a golden degree of algebraic variety over K. So K is a field of character 0. Okay. And you also have to work on some completion of this ring. So you have some filtration. And I'm sorry I have to run fast, but okay. I want you to get some flavor of this. So our zeta function will take value in this ring, which you will see later. Like we try to define measure of subset called semi-algebraic set in arc space, and the measure used to be a number, but here you have to live in some ring. Okay. And so we have to work in arc space. And this is for who haven't seen the arc space before. So you have arc space and jet schemes. I mean, the way I think it is that the point of arc space is represent. So you remember, a point is a point for algebraic variety is represented by a morphism from spec C to the variety, right? So this is similar construction here. The arc space has point represented by spec K. This is power series ring to the X, okay? And similarly, you have this jet scheme here. So now you start to see the analog between this p-adic setting and motivic setting. We also need this truncation map. So you have map between inverse limit of this. So this gives you the truncation map of arc to a jet. And you have to define measure, and I don't think I have time for this, but there is a theory for measure for so-called semi-algebraic subset on Lx, and this you can, or for me, I naively think this is like constructible set in Lx. It's like finite union or locally closed subset. Okay, but it's not just that. I mean, there are more semi-algebraic sets. Okay, but for those sets, you can define a measure, and the measure take value in the completion of quadratic ring. And I mean, here are some major theory here, and to define this zeta function, it involves to compute some measure of some semi-algebraic set in the arc space. So you will need this information here, like if you are in nice case, like for smooth case, and if the set A is a pullback of constructible set on X, on a jet scheme, then the measure is easily computed. So for nice case, it can be computed easily. Okay, and right. So this formula, and we also need some notion about the order. So given an ideal, we try to associate the motivic zeta function for the ideal. So we need notion for order, and I don't think I want to spend time on this, but this is like you have to test the order of vanishing of the function in the ideal, and right. So this is related to that, and here is the formula for the zeta function, motivic zeta function for algebraic variety and ideal I. We don't know about this, but I'll tell you a work about issue. You can compute this explicitly for monomial ideal on Toric variety, the order of I, and the contact loci. Okay, so the contact loci is the arc, the part of arc. When you take order, is equal to n. Okay, and I mean there are many information here, but the computation here is explicit for Toric variety. Okay, once you spell out the definition. Okay, but I just want you to want to mention that the way we compute Toric motivic zeta function is to use this change of variable formula. Okay, so you see Howard, Mustață, and Yuan, they compute monomial ideal for p-adic zeta function in affine space, and once you have that, you have you can similarly compute motivic zeta function for in a sense setting, okay? But for singular case, it's much difficult because you have to consider more, like for singular variety, like we have Toric variety, we have considered this Jacobian ideal for this. So we have to have a resolution, log resolution, and then compute the Jacobian ideal. Okay. So I'm sorry for that, but the key point is that this content loci. So the fact is that Jacobian ideal and this ideal shift, they are all torus invariant. Okay. So these are monomial ideals, and in the local resolution, what we do is we look at monomial ideal on each affine chart. We look at monomial ideal on affine space. Okay. So we sort of do the computation for like motivic zeta function for Toric variety. We sort of do that under resolution. So we sort of use the result in the smooth case. Okay. So this is the idea. And I think one can spend time on this. I mean, Ishi has work on the arc space of Toric variety, which tells you how to analyze the content loci of an ideal shift. Okay. So I don't have time for this. But let me. Right. So sorry, I'm too slow for that. So there is a. So the torus act on the Toric variety. So the arc space of the torus also acts on the arc space of the Toric variety. So you can have a similar oblique correspondence like this. And we have notation. I think we all have notation. So given an arc, you have an oblique like this, and this corresponds to some vertex in this set. Okay. And for vertex on this set, you can easily compute the order function that I didn't define, but for Toric variety, it's like already it's the inner product. Okay. And right, and you decompose those content loci into this orbit, and you compute the measure of each orbit. And this is actually explicit. Okay. So you compute the measure of this orbit, and you sort of sum them together, and that gives you the formula. Okay. So sorry, I have too much detail here. So right. So here the orbit. Many orbit, like when you take measure, many orbit has measure of 0. Okay. So okay. Sorry. Right. So let me just show you what the motivic zeta function look like. So you see, it's a sum of this content loci, and you have to L. So here, L to the negative ns, you sort of look at this as a p to the negative ns in a p-adic setting. Okay. And as I say, you decompose the content loci into orbit, and then it's written in this form, so it's measure of the orbit. And here is the pairing, like V pair with the minima. The pair with every lattice point on the ideal. Okay. And you can easily compute the measure of an orbit by here. It's not hard. I mean, if I can do it, I think you can do it. And so you sort of sum them together, and this gives you a formula like this. And you sum them together, you get a formula like this form. So this is for monomial ideal in affine space. you have this form. I didn't talk about Jacobian, so this is only for affine space. Okay. So you see, you have a like infinite sum, but this is a theorem of Budur-Mustață-Saito and Yuan, that as long as you have sum like this and V is in some normal semi-group, you can always write this as a rational function. And the pole, okay, the pole has to do with the normal fan of the monomial ideal here. The pole, okay, the pole of this zeta function has to do with the normal fan of the ray generator of the normal fan of the monomial ideal here. Okay. And that information can be used to compare the pole of zeta function here and the B function for the monomial ideal in affine space, right? And for toric then, once you spell out the Jacobian issue here, you have similar formula. Okay. But I'm sorry, I don't have time but maybe in the last minute, let me show you the example that why on toric variety the conjecture is false. And sorry, so should be later. So it's our favorite example here. So but since you probably don't know anything about this, but we have this cone, and you can. So you do resolution, and then you compute, and each ray in the resolution produce a candidate pole, okay? And you find if the ray. So here's one comment here. So if the ray, so there's a ray -2/3. This ray, this pole does not come from a ray of the normal fan of the ideal. This can only happen for singular toric case. Okay. And that actually gives you a pole of zeta function, but which is not the root of B function. You can prove that. Okay. And I think I will just stop here and then thank you. And today is Father's Day in Taiwan. I don't think in China, because it's August the 8th, and it's the number 8 pronounced as Ba. So Ba, the Father's Day. Okay, so happy Father's Day. Okay.